and welcome to the online certification course on microelectronics devices to circuits. In our previous module we have learnt the second order effects which are prevalent in a bipolar junction transistor. What are these second order effects? These are those effects which normally do not show their presence, but under certain conditions of electrical parameters or structural parameters their effects are pronounced, and their effects are relatively seen or influence the electrical characteristics of the device. One of the phenomena which we looked closely was basically the concept of base width modulation effect, also known as early effect, and associated with that we found out a voltage known as early voltage. This makes the early effect phenomena makes the device behave as a non-ideal current source in the saturation region or in the active region as we say. And we have also seen that there is a multiplication of charge carriers under effectively large reverse bias near the depletion region, which results in a large change in the value of your collector current. We will start from where we have left in the previous turn and see what the other second order effects are, and also look into the typical cross section of a bipolar transistor, and then we will recapitulate this whole discussion. So, typically we would expect to see that this will be the last sort of a presentation on bipolar technology. After this we will move to CMOS technology, because that will be the next structure we will see, we will see that. So, as we left in the previous discussion, the collector current IC was equals to given as alpha n times IE, where ICO is basically my reverse bias sort of a minority current carrier concentration. So, this is basically minority carrier concentration, right, and what we are predicting is that the total collector current which is flowing through a circuitry will always be a sum of the majority current carrier contribution plus the minority carrier contribution, and this factor m is given by this term, which is 1 by 1 minus BC base collector junction, and base collector junction with a capital B to the power n, where n is basically an integer value. Now, depending on the value of m, which is basically a positive integer, we would expect to see IC to be large or small, right. We also see the fact that there is a contribution. This is basically your majority carrier contribution, right. This is a majority carrier contribution, and this is primarily the minority carrier contribution, minority, right. Now, please understand that with rise in temperature you would expect to see minority carrier contribution almost double for every 10 degree rise in temperature, right, or approximately 5 to 10 degree rise in temperature, which means that the collector current doubles itself due to minority current carriers if you raise the temperature. We will come to that when we discuss other effects in our subsequent slides. We have also considered for the time being that alpha and beta, which is basically your current gain in common emitter and common base configurations, these are primarily independent of temperature. In reality not true, and that is for second issue is coming into picture. Then what is the effect of thermal effect? So, what is the thermal effect? Primarily means that, please understand, this BJT is working in an environment where applied voltages are very large. Not only that, your collector currents are of the order of millivolts. So, if your collector current is the order of milliampere sorry, then I square into R, which is basically the power dissipation which you expect to see from a device, is typically very high, right. As a result, the on chip temperature for a bipolar technology based silicon design will be relatively high. So, we cannot neglect the effects of thermal variations or effects of thermal changes onto the device characteristics. And till now we were assuming that alpha and beta were independent of temperature, but now we will see that the alpha and beta are depending on the value of temperature. Not only that, they also depend on the magnitude of IE and IC, right. We have already seen, right. Now, at very low levels of injection, what does it mean? Low level of injection primarily means that when your bias is so small that even in an NPN transistor, if the number of electrons being injected onto the base side is relatively very small, then we define that to be as a very low level of injection, right. Now, the assumption of negligible recombination in the depletion region is invalid. I will explain to you what does it mean. It means that let us suppose you were injecting let us suppose in one case when it is low level of injection, you are injecting say 10 carriers, right, 10 electrons are being injected onto the base site, right, whereas for a large injection we will have let us suppose 10 to the power 5 electrons being injected. So, if it is a 10 electron, then with respect to 10, even if there are 2 holes in the base side which is recombining, right, you still have a 20% right recombination, fine. Whereas, if you have 10 to the power 5 electrons being inserted and you only have 2 holes being combining, you can understand it is negligibly small percentage of recombination or almost 0 percentage of recombination. That is what it is written here, the assumption of negligible recombination in the junction depletion region is invalid, and the reason is that we cannot assume that the recombination current is very low, right. It will be very high as compared to your base injection current, and that is what is an important important issue. Now, we have also seen that this we have not discussed earlier, but we will make it, we will discuss this point, which you see this point, if you see very carefully, that the base conductivity modulation effect results in a decrease in the value of gamma, which is emitter injection efficiency. What does it mean that I will explain to you what does it mean. It means that let us suppose you did have a base width modulation, which means that you forward biased your base emitter and you reverse bias your base collector, and you go on increasing the reverse bias of the base collector. As a result, the effective base width is decreasing. Now, once it is decreasing, which means that the effective number of holes available is actually getting reduced, and therefore, its probability of recombination with electrons is also getting reduced, right. So, what we have learned from this is that if the base conductivity is there, it will reduce or decrease the emitter injection efficiency, which means that it reduces the efficiency by which the emitter will be able to inject its carrier onto the base site, because if it is very small, all the electrons will not be combining with holes. As a result, the emitter efficiency reduces. Now, we are 100% sure that when you are doing common emitter configuration, for example, your collector currents are very high, right, and they are very high in the sense that they are typically very high, and as a result there will be significant power dissipation in the transistor, right, and therefore, as a result there will be self heating of the device itself. The reason is that so large IC, so IC square into R, which is basically my power dissipation, this will be typically very high because your ICs are very high or collector currents are very high, and you see it is basically almost like a parabolic increase in the power dissipation. So, even if you double your collector current, you are actually making the power dissipation increase by 4 times, which is quite large power dissipation. Now, I will just give you an idea about what is known as thermal runaway, right, basic thermal concept of basic thermal runaway. So, we will discuss one basic concept which is known as thermal runaway. Now, you see that suppose you have a common emitter based configuration, emitter grounded configuration with emitter bias here, and you had a base collector junction here, and you had a RC here and RB and RE, right, and then you appropriately bias it with VCC, this is with VBB and so on and so forth, right, and you have an NPN transistor, this was your V out. Now, you see in this case your IC will be given as can be given as VCC minus. So, if you solve it from this end to this end, I get if assuming that IE is the current. So, VCC will be equals to ICRC, right, plus VCE, which is VCE, this is VCE, right, VCE plus IE RE, right. Assuming that the base current is very small, I can assume simply that IC is approximately equals to IE, and therefore, I can write down VCC minus VCE divided by RC plus RE is effectively equals to IC, right, approximately equals to IC. VCE is typically 0.2 or 0.3, this will be around 3 volts. So, 3 minus 0.2 divided by few kilo ohms, some kilo ohms. So, this will be of the order of few milliamps, right. So, it will order of few milliamps current. Now, what happens is that this I C square into RC will result in power dissipation across this resistance. So, there will be a power dissipating, right. As a result, this transistor will start get heated away, right, and there will be heating. So, what is also known as self heating. We will explain to you what is self heating is. So, as the temperature rises, please understand that by my previous discussion just now, my minority current carriers almost doubles for every 10 degree rise in temperature for minority, not for majority, please understand. For minority carrier doubles for every 10 degree centigrade rise in temperature, right. So, if a so you have increase in power dissipation which results in increase in temperature. This increase in temperature results in increase in minority carriers. Now, IC overall current will be made up of IC majority plus ICO or ICO minority. Now, though this is constant, but this every times doubles itself, which primarily means that your IC will again increase with temperature. As IC increases, IC square into RC will also increase. So, more heating effect, more temperature and more IC 0. So, this is known as, so a time will come when IC will be so large that it will destroy the BJT itself. So, there will this phenomena is known as thermal runaway, right. So, this phenomena is known as basically known as thermal runaway. So, this is thermal runaway or self heating issues, right, and therefore, this thermal runaway gives you a large amount. So, in the devices designed for high power application, the transistor is mounted on an efficient heat sink for the reason I just now discussed with you, so that the thermal energy can be transferred away from the junction, right. So, as long as you are able to shift the thermal energy away from the base collector or base emitter junction, we would expect to see no rise in the minority current carriers because of temperature, because you are able to shift the important or the major part of our power dissipation or temperature rise away from that. So, if you have a heat sink which is working as a very good heat sink, that will help you to remove the power very fast away from the emitter base junction. This is what I was saying, that if you allow, therefore, if the temperature of the device is allowed to increase due to power dissipation or thermal environment, the transistor parameter changes. So, your alpha and beta are a function of therefore temperature, right, and current gain increases. As we discussed, we will not go into details of it, but the most important parameters are carrier lifetime and diffusion coefficients. Also, we have seen that as the temperature increases, the mobility actually falls down, right, and because this is very simple, that as the temperature increases, the lattice itself starts to move across its mean position, right, because of high thermal energy. As a result, electron travelling across the lattice gets scattered by collision with these lattice atoms. As a result, the mobility falls down. So, higher the temperature, the mobility starts to fall down, and this results in a lower mobility, and therefore, when you talk of drift your drift will be equals to, so velocity of the carriers will be mu into E. So, as a result, when mu falls down, velocity falls down, and therefore, the current is reduced drastically, right. The diffusion coefficient of holes and electrons also decrease as the temperature increases, thereby causing a drop in beta due to increasing transit time. I think I will make it clear to you what do I mean, but what do I mean to say by that. It means that as your temperature rises, right, the diffusion coefficients actually starts to fall down. So, when that happens, you have, because it primarily means that d by mu is constant, Einstein's relation. So, when d starts to drop down, mu also has to go down to make this ratio constant. So, when mobility drops down, it increases the transit time, right. When it increases the transit time, the beta actually starts to reduce. The beta is basically the current gain. Why current gain starts to reduce? Because now, since the transit time is lowered, then within the same amount of time, lesser amount will be charge will be transferring from emitter to base. So, your overall collector current will reduce, and therefore, your gain will reduce, right, and therefore, and that is the reason why you have a reduction due to increasing transit time as the temperature increases, right, and this is one of the problem areas which people face in this thing. Now, thermal runaway is a standard problem area, and if circuit is not designed properly, you will have a thermal runaway which will make the device non functional and will burn up within a very short period of time. As I discussed with you, runaway of the collector current can be due to overheating and the destruction of the device, right, and this is what leads to final destruction. Let me get to the third second order effect, and that is base resistance emitter crowding. Now what happens is that we are assuming that the cross sectional area of the NPN transistor, emitter base and base collector junctions, are relatively small, right, and therefore the flux of electric field is almost constant across that emitter base or base collector junction, right. That is true even if you have very small junction areas there, but if the junction areas are relatively large, typically very large, then you do have a non uniform current density, which means that the flux lines are not uniform across the interface, right. We will not get into details of why is it like that, but that is the reality, you do not get it, and therefore the current is not equal across the interface through the base layer. This is basically known as base resistance, or base resistance increases in that case, right. So these are the three major second order effects or second order phenomena which people have seen across the board, and its removal is quite it's quite important. Early voltage or base width modulation effect can be removed by using the doping concentration on the base side much relatively higher as compared to collector. This is one thing. The second thing is how do you actually go for thermal runaway removal? Well, there are standard stabilization techniques by which we can actually have circuit level manipulations to reduce the thermal runaway or almost remove the thermal runaway, and for the base splitting and emitter following, we require to make the emitter base junction and base collector junction area, cross sectional area, as small as possible. Now let me just finish off this bipolar transistor lecture by giving you an effective cross section of a bipolar device. This is your emitter base junction. If you look very carefully, it is base, emitter, and this is also your, so this is a collector, this is your base. So you have got two bases connected back to back. So this is one base, and therefore emitter base collector and emitter base collector. So you have got two transistors in series sort of, and their layout looks something like this and this, right. So we will not go further detail than this. It is available in standard textbooks for understanding purposes and gives you a detailed analysis about the BJT as such, right. We therefore recapitulate the bipolar technology in a detailed manner, which we have already seen. We have seen therefore that the bipolar technology can be used as an inverter to make it saturation, to go to saturation and cutoff. Second order affects the performance of the behavior of the device, right, and it degrades the behavior of the device, it degrades it, right. Base region is always lightly doped. Carrier mobility decreases with increase in temperature, we have seen that. As we discussed earlier, that in order to remove thermal runaway, designer has to use heat sink, and proper heat sink design is an important one, and structural effects are important to determine the operation of the device, which structural effects primarily mean how what is the cross sectional area of the base emitter and base collector junction, right, and these are important. So this takes care of our understanding of typically the first part of our of the lecture series, and this was still bipolar transistor. We will, and it takes care of basic understanding of bipolar, the parameters of bipolar transistor, various configurations of bipolar transistor, how do you calculate current, and therefore what are the second order effects prevalent in a bipolar transistor, and that has been discussed in these set of modules. In the next module or the next lecture, we will be going through or going ahead with CMOS technology or a MOSFET technology, right. With these words, let me thank you for your patient hearing. Thank you.